bear with me for the derivation. It might be boring a little. Okay, so this will be my equation for the lateral motion, that is in the y direction, right? Now, if we want to write it in terms of a state space model, we want the relation to be of the form like x dot is equals to something into x plus something into a constant term. So I hope you are familiar with what is a state space model, right? What is state space representation and so on?
Yes, Abhinav, we are familiar.
Okay. So I'll convert this into to easily write the state space form. So my states will be Vy, one that is one of the states, and the other will be R. R is, as I told you, it's the yaw rate. So I'll use Vy and R as my states. So now this equation I can rearrange and get the form. So Vy dot equals to, I'll just send this here and divide my mass, so I can directly modify it. So it will be m, this is equals to minus Cf plus R into m into Vx plus, there won't be m here, yeah. What I did is I just moved those terms here to make it look in that state space form. So if I now choose comfortably the Vy as one of the states, I have the form, it appears in the form of x dot equals to a into x plus b into the input term du. So now similarly this is for the lateral translation. Similarly for the yaw motion, that is the rotation about the z axis, also if I do the same exercise, I can get the yaw rate in this form. So minus Cf into Lf minus Cr into Lr so this will be my governing equation for the Vy and R. So now I can directly write the state space uh, representation. So that will be is equals to I suggest that you after session, when you go home, you can maybe revise it in detail so that you'll get a clear understanding of how, I mean, which parameters are affecting in what way. Finally, we'll get the transfer function that will give us a broad picture of like which how the response is from the input. But to understand the internal mechanics, it is a good exercise to try out the derivation and see for yourself the internal parameters as well.
Yeah, Abhinav, got it. Sure, we'll do that.
Yeah. So this will be my, which matrix is this? This is my A matrix. So into Vy and R plus B times the input. So input is my, the steering input, that is my delta. So it will appear in the second term like this. Delta. So this is my state equation. Next will be the output equation. So output, if I consider, so I want to model output as just the yaw rate, because finally I want to get the heading angle, and heading angle is just the integration of yaw rate. So for that I want to extract only the yaw rate from this. So how will I extract this? So I can, because the states are very easily situated, I mean they themselves has the R term, so I can directly plug 0 and 1 to get the output of R plus D will be 0. So now I have my state space representation. So ultimately, as I told initially, our model, we want the input to be delta, and then output will be theta. In terms of transfer function, if I say, it will be in terms of S as a S function. So now, if this is my bicycle model, so this, in my bicycle model, I give my delta as input and theta as output. So R is the yaw rate. So what I'll do to get the so the value of theta, I'll I should integrate the quantity physically is integration. So once I get the transfer function of R, so integration in term in terms of the Laplace will be, I can just do theta will, sorry, theta of this will be S into R of S, right? So now uh, then oh, I'm sorry, it is reverse. R of S will be S times theta of S. So now once I get the transfer function of R, if I get the transfer function S to get the theta, so now I have the state space form, right? So if I have a function, I mean a state space representation of x dot equals to ax plus b and y equals to cx plus du. You remember how we convert state space into transfer function? I want it in the form of y of s by uh, u of s equals to something, the transfer function. So how we convert state space into transfer function?
There is a formula no, a into I minus something
Um,
inverse and then plus
yes,
something. I just
yes,
forgot the
yes.
formula, but that is a form if I'm not wrong.
Yeah. So here when we want this kind of state space model to go into a transfer function, so what we do is the y of s by u of s will be c times s times I minus a whole inverse plus d. Right. So now if I apply that for this case, what happens? My so y of s is here, r of s, and then u of s is delta of s. So apply this and then finally get the transfer function. So in that transfer function, I'll give the all the required values of the CF, M, and so on, and finally you could get the transfer function of the RS by you'll get R of S by delta of S. Right. Once you get this transfer function, what you'll do is you will get theta of S by delta of S by dividing this by okay, this is how you get theta of S by delta of S. Now once you get this and substitute all the parameters like this length, the stiffness, the mass, and so on, you will get the transfer function as proper with proper numbers and so on. So once we get the transfer function, what we'll do is we'll first see the step response, then find the design the P and PI controllers, right? So for that I'll upload what are the requirements. So for this case we have that the maximum peak overshoot, I think I'll have it in the presentation. Okay, no problem. I'll upload it in the classroom. So we have the conditions like the maximum peak overshoot should be less than 4%, and the design steady state error should be less than 1.5% and so on. So just like we did using the RL tool last time, we do the same thing once we get the transfer function. So this is the first part, that is without any actuator dynamics and so on. So now coming to the second part. So as you saw in the control block diagram, so we have the input as delta of S. I'm sorry, it is not S. So we have delta as input, then we have the feedback. So then we have our controller that we design. Then, so for this diagram, we had directly given the we are directly modeling on the bicycle model, right? And giving that, taking that as our final output. So now, what our steering actuator dynamics is, as the name suggests, it is actuator dynamic. So whenever we are steering a car, so we are giving an actuator to move it in a certain direction, right? So, but as we know, there is the rod of the steering is the shaft coming from the steering is not directly connected to the wheels. So there is a gear arrangement in the between the transmission, and if there is a power steering, there is assistance from that. So for all that model, we have this transfer function which directly gives you the transfer. We have here directly given you the transfer function. So if I have a block here with the steering actuator dynamics. So if I have a block with the steering actuator dynamics, now what will be my final transfer function? If I say this is g of s, and this is what I computed above. It is R of S by, I'm sorry, theta of S by delta of S. Now, to get the final transfer function, what I'll do, it is just the product g of S into theta of S by delta of S. So with this exercise, you'll get a feel of how the difference between the direct modeling and when the actuator dynamics is involved. So once, just a second. Okay, sorry. So in this exercise, when we design the PI and controllers and P controller, so last time as we discussed, we directly went to the RL tool. Then if you remember when we put the constraints, the areas where I can use, where my poles have to be placed so that that constraint will be met, have appeared with shaded color and so on. So in this exercise, to get a more intuitive sense and to make the controller design easier, because when in the case of PI controller, you saw that as soon as we added the 0 as well as the pole placement, we are struggling to find out the proper regions where it is, to vary both the variables and find out the position. So what we'll do is in this exercise, before going to the RL2 directly, we'll construct the route array. The route array will give us the, what it will give us, it will give us the possible ranges of Kp and Ki if there is a PI controller, so that the system stability is maintained. So as we have, as you know, system stability is prior important than the performance. So we'll construct, before going to the RL tool, we'll construct the route array, get the ranges of Kp and Ki, right? And then based on that, we'll vary the pole placements in the, the Kp and Ki values in the RL tool. Okay, that is a slight modification in this exercise. And apart from that, the procedure remains same. All right. So I urge you to construct these transfer functions by so next week's class we'll see how we'll do the RL tool, using the RL tool, and maybe I can go a basic of how the route array gives the ranges, and then the RL tool for the steering dynamics as well. So in the meantime, all the essential things are available for you to construct the transfer function by yourself. I'll upload the a small document with the parameter, the values of the parameters and so on. So in this week, 1 week, try to construct the transfer function. So next week I will give you, I'm not sure, I think I'll show you the actual transfer function, and then we'll try to design the PI controllers together. Okay, and before that, one more thing is yeah, as I told, we'll construct the route array in your report. It is better that you include the route array and the analysis of the ranges from what the route array says that the value of Kp and Ka for the system stability. All right. So that additional thing is present in this report. Yeah, that's all for today's class. I think if I start the controller design, it will be a separate module, and I can't finish it in the remaining time. So I think you're good to go with this introduction about the project. So you can start, modeling the transfer function, design, making the transfer function. And the next time, if you have any doubt, you can ask, and we'll work with how to design the P and PI controller. And I think once the transfer function is there, I think you can do the router analysis as well, route stability criteria as well. So try to do that if time permits. Otherwise, we'll discuss in the next week's class.
Abhinav, next week, Monday you're taking or Tuesday?
Actually, I'm not sure. I think
Yes,
Monday, mostly
It's a
Monday. Yeah,
holiday.
Monday is a holiday, right? So maybe I think Tuesday and Wednesday, I think one class sir will take and one class I will take.
Right. Okay.
Okay, and thank you for submission of the assignment one. After a long time, I'm seeing submission with no late submissions and so on. Thank you. Even I know you are packed with exams and so on. Thank you for submitting.
Thank you for giving the time also. That is the one which enabled us to submit it. I'm honest about this.
And Abhinav, one person to thank for this timeline is Mr. Arnachalam.
Okay.
He has pushed everyone to ensure that the project is submitted before 4th of April.
Okay. Yeah, thank you, sir. Thank you for ensuring that it is submitted. Okay.
Fine.
Okay, if you have any doubts, I am available. Otherwise, you can leave.
Right. Thank you.
Thank you.
Thanks, Abhinav.
Yeah, thank you, sir.
Yeah, thanks, Abhay.